Okay, looking at problems from section 4.4 when we talk about optimization problems. Here looking at number 6, it says, of all rectangles with fixed perimeter P, which has the maximum area. So here we have every single rectangle. So if I just come here and I just draw a rectangle. Okay, this rectangle represents every single rectangle that would have the perimeter equaling P. So my perimeter is a fixed number, it's P, it's a value right here. It could be 10, it could be 40, it could be 5 billion. We don't know what the perimeter is, but it is a fixed number that is set, and they say, here's your perimeter, this is what you get to work with. Let's now go through this and let's maximize the area. Okay, so we want to maximize the area. Okay, so it's always something we want to do. So basically what we want to do is we want to figure out what does the area equal, and then we're going to take the derivative of that area. Okay, in order to take that derivative, we want to have one variable, because once again we're taking the derivative of the area with respect to x. So we just want to have the one variable in here. So if I come over here and I say, okay, given every rectangle right here, x and y are my dimensions on it. So I have this dimension, this dimension. Once again, rectangles generally have two different dimensions. Otherwise, they start being considered a square. So if we look at the perimeter formula for a rectangle, we would have 2x plus 2, y. I didn't use L here, I used y. So this is y. I'm going to scribble that off. So we have 2x plus 2y. What we want to do is we want to basically write this area, which at this point would be x times y. We'd want to write this in terms of one variable, and we're more associated to x for a variable, so that's what we'll do here. So we'll take this and we'll go p minus 2x equals 2y. So then y equals p over 2 minus x. Once again, I don't leave it as a fraction, a combined fraction at p minus 2x all over 2, because when I bring it in here, remember, we're going to be taking the derivative. So we always want to have simplified terms as much as possible, because it's going to make it easier. So now that I have y, I'm going to substitute it up here, and I'm going to say area equals x times p over 2 minus x, because once again, that's what y was equaling to. Multiplying it out, area equals p over 2x minus x squared. Okay, so now we have our function. This is our area function. This is what we want to maximize, and we had our given restraints on it, and so now our function is in terms of our restraints or constraints that are on it right here. Considering this, we'll now take our derivative. Okay, please remember that p, even though it is a variable, was given to us as a fixed perimeter, so it is a fixed number. So this is just some number. Okay, it could be 14, 25 billion, it could be e, whatever it is for that number, that's what it is. So if we take the derivative of this, we get p over 2 minus 2x. Now, what we want to do is we want to maximize this. So we could look at endpoints, but endpoints would deem this being 0 or that being 0, in which then we can't have that because we aren't going to have a shape. So then our next endpoint, our next critical value here would be when we set this equal to 0. Okay, so as we set this equal to 0, we would see that p over 2 would equal to x. So x would equal p over 4. So this is what my x value would be. Okay. Now that we found our x value, we got to figure out what y is. So to simply find y, we would come back to our perimeter formula. So we would just basically come back right here, and we'd see that p over 2 minus p over 4 equals y. So y equals p over 4. So what we find out is that the dimensions would be p over 4 by a p over 4 inches, feet, whatever units this would be in. because these would be our values. So we see that a square actually maximizes the area of any rectangle, and thus we just prove that. If we go to number 16, okay, so on number 16, now I rewrote out these questions so I could explain and point out within here. So here on number 16, it talks about maximizing the volume of a box. So suppose an airline states that all baggage must be box-shaped with the sum of length, width, and height not exceeding 108 inches. So that means whatever the length, width, and height of the box cannot add together to be more than 108 inches. Sorry. What are the dimensions and volume of a square box with the greatest volume under these conditions? So something to think about here is, why would we choose square box? Well, just because in the previous problem we proved that the maximum area of a rectangle is a square, so that's why we chose a square. And remember that when we deal with a problem, we're dealing with basically a cube. So if I were just to kind of draw this out, what we have going on here is we have this box that we're in reference to, and this is what we're shipping towards. So now I can make it a little 3 more dimensional here for you with my hidden lines behind there. As we look at this, we have to consider that we want the volume of this box, but we need to know some constraints that are on here. Okay, so we talk about that the length, width, and height. Okay, so this length, width, and height, however you want to state it, this could be the width, this could be the length. Whatever is happening here cannot exceed 108 inches. So width plus length plus height has to be less than or equal to 108 inches. Well, if we think about this, if this is going to be smaller than 108, that means this is just going to be a smaller box. So we'll change that, and we'll basically state, let me get my red here, that we want to be equal to 108 inches. Okay, so if we consider this, they told us a square box. So if I come back here now and I just kind of redraw this a little bit, I'm going to have this be x and this be x. So now I got my square box. But if this is x and this is x, what is this height going to be right here? Okay, so once again we have x plus h equals 108. So h would equal 108 minus 2x. So x plus x would be 2x, then we would subtract that over. So we see now that we have 108 minus 2x. So what I did was I took this original box, which was a length, width by height, and now I converted everything to be in terms of x, because we want to find the greatest volume. Okay, so volume was length times width times height of a rectangular prism. We kind of changed that by stating that it is a square, so we had x squared times height, because we said we're going to have a square base. Once again, remembering any prism shape is going to be area of the base times the height. And then now we state that volume equals x squared times 108 minus 2x. So now that we got to this point, we're like, oh hey, we have our volume in terms of one variable. Okay, so we went through all our restraints and we dealt with that to get a volume condition that was happening on here. So what we want to do now is we want to finish expanding this. So volume equals 108x squared minus 2x cubed. And then we're going to take the derivative of this. Because once again, our system of constraints could deal at our endpoints, but this would be overall cubic graph going on. Just remember that we can't have anyone being 108 or 0, so that's not really going to help us. So we're going to come in here and we're going to state, okay, our derivative now is 216x minus 2 times 3 is 6x squared. Set it equal to 0. Once again, we set it equal to 0. These are going to give us our critical values. Okay, so if these are our critical values, in the process setting equal to 0, I'm going to factor out a 6x. So if I factor out a 6x, that leaves me with 36 minus x equals 0. So that means 6x equals 0, or 36 minus x equals 0. So x equals 0, or x equals 36. Now do realize that x cannot be 0. So we come back up here and we see we have 36 inches by 36 inches. Once again, for this x in here, if this is 36, this has to be 36. Now we got to figure out what this other part is right here. So if I come down here and I take 108 minus 2 times 36, this equals 36. So we see that the dimensions, so it asks us what are the dimensions. A 36 by 36 by 36, it gives us this maximum area. And then it asks, and the volume. Okay, so what would the volume here be? Well, in this case, we would just take 36 cubed, and we would have 46656 cubic inches. Okay, and that's how we would do this problem. Once again, this was maximizing a box shape that we're given. If we move on to my last problem, a little bit more of an application problem, actually kind of interesting on here. It's number 37. Okay, so number 37 talks about basically a power company overall. Okay, so this power company has an island it needs to get power to. Okay, so this island is 3.5 miles from the nearest point on a straight shoreline. So once again, the shoreline is going to be straight. So the nearest point is going to be perpendicular to that. You can go back to geometry class if you need to verify that. That point is 8 miles from the power station. Okay, so once again, I have it drawn right down here. So we see we have our power station over here. We have our island here. We have 8 mile distance here, and then here, once again, this is going to be a perpendicular. So let me just draw that in with an orange here. This is going to be perpendicular right here. Once again, only because this shoreline is straight. If the shoreline was crooked, everything, we would have so many different scenarios I could go into this. So we tend to see this is once again ideal. So this utility company plans to lay electrical cable underwater from the island to the shore, and then underground from the shore to the power station. Now, it costs $2,400 per mile to lay cable underwater and $1,200 per mile to lay cable underground. So we see that underground is cheaper than underwater. At what point should the water cable meet the shore to minimize the cost? So basically what we're trying to state here is we're going to be laying some cable. Okay? So they're going to be laying some cable along here. But there's going to be some point where they're going to be better off going and laying that cable in the water rather than go all the way over and then all the way across. Okay? So as we consider what's happening here, we got to be thinking about what values do we have going on? What are we working with? Okay? So once again, we're trying to minimize our cost. Okay? So our cost function is what we're trying to minimize. So if we think about our cost function is going to be 2,400 times, I'm just going to go underwater distance, plus 1,200 times underground distance. Okay? So we're going to have to pay $1,200 per mile here and then $2,400 per mile there. We want to try to figure out, well, how far are we going in here? So what I do is I took a look at this and I said, well, let this be my x distance right here. Okay? So that means that breaks my 8 miles up into 8 minus x right here. Now the reason why I had this be x is here is because I have a distance right here that I need to find. If we think about this, this is just a right triangle, so the Pythagorean theorem applies. My hypotenuse would be the square root of 3.5 squared plus x squared. Once again, the sum of the legs squared, and then take the square root of that would be that hypotenuse. So as we're looking at this, now we have our distances. So we can come here to our cost function, and we can state that we have 2,400 times our underwater is the square root of 3.5 squared plus x squared, and then plus 1,200 times, here we have 8 minus x. Now I could have had this be x, but then this would have meant this is 8 minus x here, and then that would have brought in here, so that's why I had x be the part that dealt with both these distances rather than trying to compound in there and be more complicated. So as we look at this, we can kind of consider, we're going to have to take the derivative of this, because once again, we want to minimize the cost. So once we get our cost function down into terms of one variable, okay, so our cost function in terms of one variable, we can take the derivative of this to minimize or maximize or minimize what we're trying to find. So by taking this derivative, we notice on this first one here, we're going to have a chain rule. Simply stated, because of everything, we have a function within a function. So if we take the derivative of what's inside, we see that we would have, when we write that 2,400 times 2x times the derivative of our overall function. So square root function is going to be 1/2 times what's inside to the negative 1/2 power then. Plus, if we look back here, this would be 1,200 times 8, so that would be 9,600. Derivative of 9,600 would be nothing, and which then, so now we would take 12, so I'm just going to go 9,600 minus 1,200x. So taking the derivative of minus 1,200x would be plus, I'm just going to go negative 1,200. I already have my plus sign written there, so we'll just write it that way. So kind of simplifying what's happening on here, we would have, let's see, the 2's would cancel. We would have 2,400x over the square root of 3.5 squared plus x squared minus 1,200. So now we'd have to go through and we'd have to solve for x. And once again, well, we would set it equal to 0, and then we go through and solve for x. In this process of solving for x, we would add 1,200 over, then I'd multiply over by this, then divide back over by 1,200. Given that, then we would square, simplify, continue on solving for x. We would see that x equals 7 root 3 over 6. Okay, so x equals 7 root 3 over 6. So if I simplify this, that is approximately 2.02 miles. Okay, so we'll just go 2 miles for purpose of a little bit easier. So that is this distance here. So basically we see that at what point should the underwater cable meet the shoreline? 2 miles from the station. Okay, so we're seeing that x is the distance right here. So we're seeing that at 2 miles from the station, this underwater cable should reach the shore, and then they should go 6 miles right here. And that should minimize the cost of this. Once again, the solving here, I just kind of did that to save you on some time.